So good afternoon to all, and yes, Shubha Navvarsh to all of you and your family. So I hope you will celebrate today in a good fashion. Uh, okay. But we want to continue our study with the second lecture on approximation algorithm. So today we shall discuss about formal definitions and with some examples to understand what is about approximation algorithm. Okay, fine. So the formal definition of approximation algorithm could be like this. Okay, so A is an approximation algorithm if it's a feasible solution that is to the exact solution of the problem statement P. So algorithm A approximation algorithm if it generates a feasible solution. Okay, so that is very close to the exact solution of that problem P. Then I can call that algorithm to be an approximation algorithm. Okay, so we have some classifications of approximation algorithms. So discuss their one by one, uh, discuss their definitions. So first we are coming to approximation algorithm. To a problem P is an absolute algorithm. Okay, an instance I of the problem P. Okay, P. Okay, so before going to this, we just come to know here. So an algorithm, approximation algorithm A generates a feasible solution. Okay, and we have the exact solution. So these two are close to each other. So now here we want to assume let the solution let the solution generated by A, we can call it also an estimate to the solution, exact solution. A and the exact solution B this, and if star I respectively. So then we can say here, so this absolute difference between the values of f bar I, which is the estimate or the approximated solution, and f star I is the exact solution. So their absolute difference minus f star I is very close, and we want to define very close means, let's say less than equal to some positive constant. A is some positive constant. Okay, so this is an absolute approximation algorithm. Okay, okay, so next we go for epsilon approximation. Before that we shall have Fn approximation algorithm. To a problem instance, problem P is approximation algorithm for an instance I of the problem P so for instance I would write, so okay, if for an instance of the problem statement P, it's follows follows difference if I and if star I is less than or equals to some function f. Okay, assuming absolute difference, I mean the fractional absolute difference divided by if star I সরি একটু হ্যাং করে যাচ্ছে, একটু হ্যাং করে। Okay, so then we come to our next class definition, that is here E, actually it is epsilon. So epsilon approximation algorithm. Algorithm A is epsilon approximation algorithm. If it's an property of Fn approximation algorithm will be satisfied by epsilon approximation algorithm, and addition to that such that such that if bar I minus f star I divided by f star I is less than equal to not if this is rather epsilon, where still f star I is positive. Okay, and here epsilon some positive constant. Okay, so next we come to the next definition, that is approximation scheme. An algorithm, okay, man, e approximation algorithm, which is denoted as like this. Okay, an approximation scheme if for every instance e greater than 0, I mean epsilon greater than 0. Okay, this is basically epsilon greater than 0. Okay, so if for every, okay, every problem instance I of problem P, and for every epsilon greater than 0, okay, epsilon of E, it's a solution such that the following condition is satisfied. Okay, and that is okay. So we are denoting that sorry, uh, okay. So where this is some constant. Okay, fine. So for every, here we will find, we just have to satisfy this condition for a single, we have to find a single epsilon value which is positive. Here for every such epsilon we have to satisfy this condition. where epsilon bar is another positive constant. Okay, so next we come to a very important, the most popular definition, which is polynomial approximation scheme, FPAS. Okay, an algorithm A is polynomial approximation algorithm, and approximation is an approximation scheme. All the properties of approximation scheme should be satisfied this type of approximation scheme, and plus that, okay, that computed in computed in such that, okay, such that its computational time is a polynomial problem size, let's say n, and by epsilon. So the 1 by e means 1 by epsilon. So please make a note, this e is not that e, 2.7, right? So this is epsilon. Okay. So, and we denote computational Tn equal to poly of n comma of n comma 1, right, epsilon. Okay, notation. So computational time is a polynomial of n and 1 by epsilon. So this is the most popular uh, algorithm, category of algorithm, class of algorithm. Okay. Now we go for some example. We will try to demonstrate today two example. Example one. So my reference is again Sahani. So 0 by 1 knapsack problem. The problem is following given that given 0 by 1 knapsack, and that is P 1 W1 W2 1. Okay, then we are given that what is a knapsack 0 by 1 knapsack problem. So I think I don't have to write the mathematical model of 0 by 1, you just recall it. Okay, okay, let me write that. We know that uh, 0 by 1 knapsack we have to find an optimal solution, optimal vector of xi's. Okay, so argument of max of summation of pi I, where I is 1 to n, we have n number of objects are there, n number of objects of which profits are p1, p2, pn. Okay, and their corresponding fractions are x1, x2, up to xn. Then we have to maximize this summation function of the profit, which is the cost function. The argument x for which this becomes maximum is actually x0. So this is that mathematical model, and subject to the following restrictions, which is summation over w I xi. Okay, it should be less than or equals to m. Okay, where I is equal to 1 to n, right? And also we have uh, x0 xi is now equal to, so this is fine, and m is the capacity of the knapsack. So this is 0 by 1, right? Okay, sorry, 0 by 1. So xi belongs to state 0 or 1. Either xi will be 0 or 1. Okay, so this is fine. So this we know that this is the 0 by 1 knapsack problem model. So we take an example, p1, p2 equal to 100, 20. So two objects are there, of which profits are 120. Their corresponding weights are 4 and 1, and the capacity, knapsack capacity is given as 4. Now how can we find a solution, a feasible solution? So one such, in this case, as it is a 0 by 1 knapsack problem, so you can find a knapsack, optimal solution as, you find optimal solution as, what is the optimal solution you can find out here? P1 comma P2 120, right? So we may take, x1 equal to 1, x2 equal to 0, or x1 equal to 0, x2 equal to 1. These are the only two possibilities. So if I take x1 equal to 1 and x2 equal to 0, then P1 x1 will be equal to 100 and W1 x1 will be equal to 4, and that is satisfying this condition. Okay, but if I take x1 equal to 0 and x2 equal to 1, I shall get the profit as 20 into 1, that is 20, and Wixi, summation of Wixi will be equal to 1 into 1, which is less than or equal to 4. So out of these two possibilities, in one case we are having profit 100, another case we are having profit 20. So the first choice is the optimal solution. That means the optimal solution is given by x0 xo is equal to 1 comma 0. This is the optimal solution. Okay, so for which we have as that profit P is 8 into 1 plus 20 W1 xi 4 into 1 plus 1 into 0, that's equal to 4, less than or equal to m. Okay, so I hope you are getting that. Okay, so this is satisfied, so this is the optimal solution we can find out from here. Okay, but at this situation, now this is one case, let the problem of the 0 by 1 knapsack is as follows. Okay, P2 is equal to R. This is very important part which I am now trying to make you understand, explaining. Okay, so very good observation. We can come up with understanding. So W1, W2 is given as equal to let's say 1 over R. Okay, and let's say we are also given that m equal to. Okay, so in that case, if R greater than 2, if R is greater than 2, if R is greater than 2, see what we can see. So P1 right, r is greater than 2, r is greater than 2, so the profit corresponding to the second object is more than the first object, more than that of the first object, and the solution is either 1 comma 0 or 0 comma 1. So that means one object you will take, other will you will not take. So which object we have to select? Means one object out of two objects, exactly one object out of two objects we have to select. Otherwise not. Okay. So in that case, whether you will select the first object or second object. So if r is greater than 2, obviously you will take the second object. Okay, to maximize the profit. And in that case, wixi, summation of wixi will be equal to r, only r, and that is satisfying r, right? So we can, if if this is 2, r greater than 2, x optimal is equal to 1. Okay. Okay. But so we have two possible solutions. We have two possible feasible solutions. One is 1 comma 0 and another is 0 comma 1. Now if r is greater than 2, then x0 will be equal to 0 by 1. Okay, so from this case we can understand that an approximation algorithm, you have designed some approximation algorithm, and that algorithm generate a feasible solution either 1 comma 0 or 0 1 or 0 comma 1. So an approximation algorithm can generate a solution 1 comma 0, but that is not optimal. It's possible. One may counter that. So if I don't go for approximation algorithm, if I go for approximation algorithm, I may not get an optimal solution. Okay. For example, this case. Okay. So, but that is not optimal. Okay. And let's study a little bit about this approximation algorithm. Uh, Also, we can observe the summation of pi equal to, in this case, if I take 1 comma 0, then it is 2 into 1, and that is 2. 2 into 1 plus r into 0. And also we have w to, it's 1 comma r given, so 1 come into 1 r into, okay, and that is less than or equal to 1, so that is less than or equal to, so that is so the condition is satisfied. Okay, because r is greater than 2. Okay. So now from here, next what we can conclude, So we can conclude that what kind of approximation algorithm is this? Absolute, Affine approximation, or epsilon approximation? Let's study about that. Okay, so for that purpose, our exact solution is in this case the optimal solution. The optimal solution is 0, 1. So 0, 1. In that case, profit is equal to P. Okay, so let's say the exact solution, the exact profit solution is equal to R, and the generated solution, profit solution is 2. Okay, so in the next line what we can write, that is modulus of f hat I if star I is equal to modulus of, you know, 2 minus R. Okay, how can we write that? So modulus of R minus 2, it is, you know, if R is greater than 2. Okay, so if R is greater than 2, this can be written as R minus 2 because of the absoluteness, absolute function, so R minus 2. And R minus 2 is greater than or equal to 0. As R is greater than 2, so we can write that R minus 2, is greater than 0, greater than 0. That means can't find any lower bound to the above difference, and hence algorithm A is not an absolute algorithm. So this is the justification. Okay, with the help of this example. Next we go for the fractional absolute difference. Now, if bar I minus f star I divided by f I you know, is R minus 2, 2 minus R, and next divided by R. Okay, so in the next line we can write that R minus 2 by R. Then we can write that 1 minus. So now what can we say about this expression? So as R is greater than 2, so 2 by R is less than 1. but 2 by r is greater than 0 because r is a positive quantity. So this value 2 by r is lying in the range 0 to 1. So then 1 minus 2 by r will lie in the range 0 to 1. Okay, so we can say that it is less than, and also it is less than 0. So this 1 can be treated as the function fn equal to 1. Okay, so in the next, so A is one approximation algorithm. 1 is the fn approximation algorithm. Now the third case, let's check for whether the algorithm A is epsilon approximation algorithm or not. Next, we check that this okay, 1 minus 2 by r, okay, is not less than, it's less than 1, fine, but can we say that it is less than epsilon for some epsilon greater than 0? Not can't be always true. This is not always true. Epsilon greater than 0. Okay, so it is less than 1, but the value may be 0.9, and epsilon greater than 0, epsilon has to be very close to 0. Okay, so this is not always we can say. Okay, so this is can't be epsilon approximation algorithm. Can't be always true. Yes, we may find, okay, interestingly, we can, this is not can't be true. This is for some epsilon one. Okay, so this is true for epsilon less than 1. So can't be true for for epsilon. That means we can find some positive values of epsilon greater than 1 for which this condition is not satisfied, and hence A is not an epsilon approximation algorithm. I hope now it is very clear. Okay. Fine. Okay, so this is our first example to understand the class of approximation algorithms, absolute, affine approximation, or epsilon approximation algorithm. So it's 1:34. So let's take another 5 minutes to discuss about planar graph following. Now let me talk about what is a planar graph. Okay. So planar graph obviously it's a simple graph. Okay, a graph finite graph is planar graph if graph can be drawn on a plane that its edges meet only at vertices. Example, we have a K4 complete graph K4 complete graph undirected graph. Okay, so this is a K4 complete graph. Planar graph. So because why? Because can we draw such a graph on a single plane? So let's try to draw this. Okay, so we have 4 vertices. This is not the planar representation because here these two edges are intersecting at that point. That means these edges are meeting at some vertex, at some point vertex, which is not a vertex belonging to this graph. So this is not allowed. We can't draw these edges like this. Okay, if I construct the planar representation of the graph, this can't be a planar representation where the edges are intersecting at some point, let's say some vertex, which is not the vertex of this given graph. Okay, so at least this can be an edge. This is another edge. This is the third edge, fourth edge. So let's say we can also draw this edge, but the other edge is not possible like this, but I can construct an edge like this. Okay, so this is one planar representation of K4. Representation of, that's why we can say that K4 is a planar graph. Okay. Example 1. Next we go for another example, which is not a planar graph. Non-planar graph. So this is about a planar graph. So we can take K5 complete graph. If you have any question, you can ask me. recording is going on. Yes. Okay, so this is a K5 planar graph, a K5 graph, and we can show that this is not a planar graph. Let's try to construct its planar representation. Need not to be complete graph. No, no, no. We are taking some example. All planar graphs are not complete. Okay, that's all. Next, we can construct this graph, these edges. Okay, fine. But see, I just want to show you here. So, this edge we can't draw in this picture. Similarly, this edge is also not possible to construct here. Okay, we missed a edge here. Sorry. So this edge is not also possible to draw here. Okay, so this, right. So these three green colored edges are not possible to draw inside this pentagon. Okay, what we can do, that is I can do this green colored. Okay, so let me erase this. K5, and I just want to show you the which edges are being successfully drawn. So this is successfully drawn. Okay, and then we can also construct this edge or this edge. Okay, so I can also construct this edge like this. That means this edge is already drawn, green colored, and the edge which is left, that is this one. Let me color that with the red color. Okay, so this edge, if I want to construct that part, okay, from this vertex to this vertex, I have to go somewhere like this, and there's the problem. These two edges, the green and this red, are meeting at some vertex which is not belonging to the vertex set of the given graph. So this is not possible. Okay, so this is not possible. Okay, let me draw that, then you can understand. Okay, so and green colored edges are meeting vertex of the given. Hence, okay, yes, আর কিছু লেখার দরকার নেই, এটুকু বলেই হবে. So hence the K5 is not a planar graph, it's a non-planar graph. Okay, so this is the planar representation of K5. Planar representation. I hope you got it this. Okay. Now come to the conclusion of the class with this thing, approximate algorithm of planar graph coloring. Planar graph coloring. Before that, let me uh, tell you some important fact. Okay, that is, we have a theorem. The facts. The facts are, number one, if to v comma e, the graph. Okay, be a graph, and it's a be a planar graph. Okay, uh, and we have to okay, let G be a planar graph. Okay, it's a planar graph. So if fact number one is if V equal to an empty set, there is no vertex in the graph. So 5. Then G is 0 vertex color. If there is no vertex in the graph, no color is required at all for graph coloring. Okay. So we have set of edges is an empty set. There is no edge. G is one vertex coloring. Okay, so these are two important facts, and then we have a theorem and that is is a bipartite graph, also be taken as a fact, third fact. So if G is a bipartite graph, then G is two vertex color. Okay. Okay, you can also include this as a third fact. So let me include that. This is the third fact. Okay. Next we can have a theorem. Theorem is which is theorem. The theorem, okay. The theorem is planar graph is four vertex color. Very powerful theorem, and it has been developed. It means it has been proposed in 1976 by Hackett. Probably spelling I don't know, CK or K, whatever. 19 very popular theorem about planar graph coloring. So every planar graph is 4 vertex colorable. Earlierly the theorems which had been proposed, those were 6 vertex colorable, 5 vertex colorable, and this is the latest version of planar graph coloring theorem. Okay, so now we are in a position to write the approximation algorithm for planar graph coloring problem. Okay, the function of the algorithm. Okay, to that phi. Okay, phi means here we are checking if V contains no vertex. Okay, then simply you return 0. Contains no edge, then return 1, and else if is bipartite graph, return 2, and else if, and finally we have else part where you have to return 4, because every planar graph is 4 colorable. Return 4. This is the approximation algorithm for planar graph algorithm. We are not, and how powerful is the algorithm looking like? See, we are using the facts, and we do not have to apply the traditional graph coloring technique for, let's say, for K5, K6, or I mean all the planar graphs. Okay, K, okay, so which may contain 5 vertex, 10 vertex, 15 vertex. So if you can understand it's a planar graph, you can immediately say that it will be 4 colorable. That is the approximation algorithm. We do not have to apply coloring technique. Okay, graph coloring algorithm, traditional deterministic graph coloring algorithm, and deterministic graph coloring algorithm is an exponential one, computational time complexity. It follows. So in that case, if I apply approximation algorithm to planar graph algorithm problems, then huge advantage in terms of computational complexity. Okay. So, and for your information, just I want to convey you a message that the time complexity of this algorithm will be in the order of uh, okay. So I can, and that is, the polynomial time algorithm. So if cardinality of V is n, cardinality of E is m, so n plus n. Okay, so order of n plus n. That means in linear time complexity, the algorithm does have. It's a huge reduction in terms of complexity, time complexity of the algorithm. Okay, fine. So with this, I can wrap up the class. Also, this time complexity can be proved, though there are many things we have not done, and it's not possible to cover all the things in this course in this short time period. So it's a well, uh, this theorem, this time complexity formula has been proved. Okay, so it's provable. If you are interested, you can go for some reference and you can go for the proof. You can see the proof. So if I am done, so if you have any question, you can ask me. questions. I hope no question. We can stop recording.